Tutorial 8, Part 4, Iron-Iron Carbon System, TTT diagrams, and transformation. What is Iron-Iron Carbon System? Or what is Iron-Iron Carbon phase diagram? Why do we need to learn this system specially? It is because it describes the phase diagram for steel, and which is very, very important in the industry. So we use this as an example. Iron carbon phase diagram is shown in this picture. You may notice a few regions. The first thing is at the vertical line on the left, it is 0% carbon or 100% iron atom. At the line here, it is 100% cementite or 100% Fe3C composition. Okay, so when we go up with temperature, the first region we encountered is this region, alpha plus Fe3C, and there is a eutectic point here, and after we go up, there is austenite, and there is also Fe3C, and at this small region here, it is the alpha phase. The alpha phase stands for the pure iron solid phase, and when we go up more, it will become liquid phase as normal. Phases of iron-iron carbon steel system. Ferrite, which denoted by the alpha, is a BCC structured iron, and if you still remember, which is the small strip at the left of the phase diagram. Austenite, denoted by the gamma, is the FCC structure. It can only exist at a higher temperature. And by ferrite, when ferrite transforms to austenite or G iron, it will transform at 912 degrees Celsius. Cementite, it is at the rightmost vertical line, which is Fe3C. Pearlite is a uniform mixture of alpha phase ferrite plus Fe3C, and pearlite composition is 100 at the eutectoid point, and also in eutectoid steel. As it is eutectoid, pearlite will have a laminar structure, as you may guess. Hypoeutectoid and hypereutectoid steel. As I mentioned, there is a eutectoid point in this system, which is indicated by my pen here, and therefore we can define the hypoeutectoid steel and hypereutectoid steel by draw a eutectoid line. At the left of the eutectoid line, it is hypoeutectoid steel, and at the right of the eutectoid line, there is hypereutectoid steel. By definition, hypoeutectoid steel consists a little bit more of alpha state, and hypereutectoid steel consists a little bit more Fe3C than eutectoid steel. And using a similar argument used earlier in this phase change phenomena in terms of the microstructure, for hypoeutectoid steel, when it enters this region, there will be a first formed some primary alpha phase grains, which is denoted by the red region shown here, and it will grow along the original green boundary of the gamma phase. Gamma phase is the austenite, and afterwards all of the rest austenite will change to pure pearlite. Pearlite is a mixture of Fe3C, which is here at this line, and Pearlite, which is here. For hypereutectoid, the argument is also similar, but this time, primary Fe3C will form first, and then it will go along the boundary, the original boundary, and afterwards the pearlite will form. And in terms of the eutectoid wordings, eutectoid A means the alpha state formed at eutectoid temperature, and the pole-eutectoid alpha means the pole-eutectoid phase formed before the eutectoid temperature, which is this line, and also this line. And yes, this eutectoid and pro-eutectoid are defined in a similar ways. Of other alloy elements, such as chromium and nickel, brings changes in the binary iron-iron carbon phase diagram. As it may decrease or increase the eutectoid temperature, it stabilizes ferrite or austenite. And it also usually decreases the carbon content of the eutectoid composition. And that means it shifts the eutectoid line towards the ferrite side. TTT diagram for iron-iron carbon system. As I mentioned, TTT diagram will be introduced in this part, and I will use the TTT diagram for iron-iron carbon system to illustrate my description, as TTT diagram for this system is the most commonly used, and it is also used in textbook. Iron-iron carbide eutectoid reaction is austenite, denoted by the gamma phase, is changed to ferrite plus cementite. And if we consider the rate of transformation, we need to use TTT diagram, and which is here. Here is the TTT diagram. At this eutectoid reaction, we have the following TTT diagram, and you can see that it is first from austenite gamma phase. Afterwards, if we wait long enough, it will transform to fully pearlite. At a lower temperature, it will transform more quickly, as shown here. And there is three curves: begin curve, completion curve, and 50% completion curve. Begin curve is 0% pearlite. Completion curve is 100% pearlite. At 50% completion curve, as defined, it is 50% pearlite. And just above eutectoid temperature, as you may know that austenite can never transform to ferrite and cementite just above this eutectoid temperature, as defined in the eutectoid reaction for iron-iron carbon system. Initially, 100% austenite. What will happen in terms of composition if held at these following conditions: A, B, and C? For A, at 680 degrees for 100 seconds, it will finally be 50% pearlite and 50% austenite. Okay, so how can we know that? We need to use rulers to first find the respective temperature first. Do use ruler, which is very, very important. Draw a line, which is the temperature line. Oh shit. And draw a timeline, and their point will meet at the point where the point describes its composition at that specified time and temperature. And according to this graph, it is just at the 50% completion curve. That means it will contain 50% pearlite and 50% austenite. Okay, for B, at 600 degrees Celsius for 100% for 100 seconds, it will be 100% pearlite. Again, draw a temperature line, draw a timeline, which is already drawn because it is the same time, and you can see that it is 100%. It is passed through the completion curve, and therefore it is 100% pearlite. C, at 800 degrees Celsius for 1000 seconds, the answer is 100% austenite. It is before because you need to notice that 800 degrees Celsius is higher than the eutectoid temperature for the steel, and that means it will never become pearlite. Note that TTT diagram is only valid for constant temperature at phase change region and a constant composition. Phase change under continuous temperature change is described by continuous cooling transformation diagrams. Microstructures in steels, Bainite, Martensite, and Spheroidite. At the different cooling rate, different microstructure will form in steel. Apart from Pearlite, there are other microstructures, Bainite and Martensite. For austenite, A stands for austenite in this picture. It is well known for you. For Pearlite, there is two types of them. At a higher temperature, they will form coarse pearlite. At a lower temperature, it will form fine pearlite. It is because at a lower temperature, the nucleation site becomes larger, but the growing speed becomes smaller. That means more and more grains, more pearlite grains will form, but it is more fine, more smaller. Bainite is at a temperature even lower than the temperature for pearlite formation. It will become bainite. For martensite, it is at a temperature even lower than bainite. It is a rapid rate transformation at even lower temperature done by some process such as quenching. You can see from the diagram here, TTT diagram here, at the higher temperature, it will form pearlite. At the lower temperature, it will form bainite. But at the lowest temperature, it will form martensite. Bainite is also pearlite plus cementite phases. And they are both laminar carbides for bainite and pearlite. But however, for bainite carbides, they will align with the ferrite crystal. But for pearlite carbides, they are random aligned. You can see here. Pearlite formation, it is laminar at a higher T. After bainite, it is smaller, the grains are smaller, and it follows the ferrite crystal. And for the lower bainite, it is even smaller. And you can use a similar argument of the nucleation of gold to describe why the size of differs. Martensite, it is austenite changed to martensite, from SCC structured austenite to BCT structured martensite. BCT stands for body centered tetrahedral, and it is a diffusion-less transformation, unlike other transformation. And that's why the transformation rate is really high, and it does requires high transformation rate to form martensite. And here is a picture describing the martensite. Martensite are those grains here, and will formed in the shape like this within the original austenite, denoted by gamma. Spheroidite. Spheroidite is a pearlite or bainite structure held at a temperature close to the eutectoid temperature for a long period of time. And due to the diffusion, the cementite will form to some shape like a sphere, and the ferrite will be the blue region as illustrated in the graph here. That's why spheroidite obtained its name, and such structure cannot be obtained directly. Properties of pearlite, bainite, martensite, and spheroidite. For ductility, spheroidite will be highest compared to pearlite, compared to bainite, compared to martensite. And the strength is just reversed. And it can be explained by the dislocation movement and the microstructure. For grain size, pearlite is largest, bainite is smaller, and martensite is smallest. And the martensite is BCT. It has a smaller sleeping mode than ferrite, which is body center cubic. You can refer to tutorial 4 for more description about the sleeping mode. And spherical cementite within the spheroidite are not as effective as laminar cementite in pearlite in terms of the stopping the dislocation movement. And that's why we put it as this way. TTT diagrams for non-eutectoid steels. And here is one example. In this example, this should be the hypereutectoid steel, as in this region, there is the addition of the cementite. And you can see that when the carbon when the steel goes from this point to here, you will first form some cementite first, and which is definitely the hypereutectoid steel, and then it will form pearlite. The rest of them will form pearlite. And we will use an example to illustrate my idea. Name the unknown phases for the following TTT diagram for hypoeutectoid steel. The first thing is only austenite will eventually transform to pearlite. Always remember that, because the reaction equation on the left hand side is the austenite, and that's why at this region it must be austenite, and also in this region it must contain austenite. And it is because this one is the hypoeutectoid steel, that means it have a slightly more ferrite. As shown here, hypoeutectoid, primary ferrite will form first. And remember that hypoeutectoid steel has less Fe3C content than eutectoid ones, and that means the another phase here is F, which stands for ferrite. More TTT examples. Consider the red root and the blue root of phase transformation. Write down their percentage of each microstructures at the end of their root. For example, in terms of C stands for pearlite, B stands for bainite, etc. And which root will produce steel with a higher strength. And assuming these two pieces of steel has same chemical composition. For blue one, it will be 50% pearlite, 25% bainite, and 25% martensite. Why? And the first root here, 50% of the austenite will transform to pearlite. Afterward, the rest of the 50% austenite, as the rows specified, will be undergo phase transformation in 400 degrees Celsius at a lower temperature. That's why the 50% of the 50% austenite will be changed to bainite according to the third line here. And the rest of them, according to this curve, will be changed to martensite. And because pearlite and bainite and martensite will not change to other microstructures, and only austenite will change in the phase transformation. And that's why you have the following composition. For the red rod, it is pretty straightforward. It is, after this rod, it is 100% pearlite. Even though it is changed to 0 degrees Celsius, it will still not change to the Martensite, because only austenite will change to Bainite or Pearlite or Martensite. And the blue rod will produce a steel with a higher strength, as it contains more Bainite and Martensite, which is much more stronger than Pearlite. And how do I produce these rods in real life? And it is related to my material processing methods, which I will describe it in tutorial 9.